chapter. And so this part of the arrow pushing is very important. There'll be many questions asked about the how does reaction taking place, what is the product, and especially predict the main product. In this chapter, the product prediction is simpler than the future chapters, because the future chapters we'll see there are many other reactions competing. And in today's class is fairly easy. And the last part, design synthetic pathways. The organic chemistry to the higher end in the studying, it is about being able to use the reactions we learned and the reactivities. What kind of a reactant promoting certain kind of product. We use this knowledge to design certain ways to make new molecules. And organic chemistry, very different from the inorganic. It is, we use organic molecules to design medicine, drugs. Because our human body, most molecules is organic molecule. Well, except water. The 30% body weight is organic molecule. And those organic molecules to interact, to treat disease or doing some kind of manipulation, it's all require organic molecule to get in the body and take effect. And to design the organic molecules to work on our body or from whatever animals, it is one of the higher goals in the study of organic chemistry. Understand how does molecule work together. And the main purpose for this class, it is understand the reaction mechanism and be able to predict which ways and what product you get from the reaction. The nucleophilic substitution reaction. Substitution reaction in general looks very familiar, looks kind of like the a double displacement reaction in general chemistry we learned. And the generic formula is the A is a species react with a molecule with B and C, C being the leaving group. So the A will form bond with B, C will leave the structure and become the product. It looks like it's just either single displacement or double displacement. So the example, and here's we have a alkyl chloride react with hydrosulfide. I can call it hydrosulfide. This is a nucleophile because there are 3 lone pairs on the sulfur, and it attacks the electropositive carbon, and the attack form bond between the sulfur and the carbon, and the chlorine, being the leaving group, becomes the chloride ion. This reaction has the nucleophile and electrophile, and this is positive. The negative charge is the nucleophile attack the positive carbon, and the electrophile is the positive charge, slightly positive charge carbon, attracting the lone pairs from the sulfur. So it has both. It's a very common organic chemical reaction, and the reaction process relatively simple, easy. And so the reaction substitution happens. It is the nucleophile attack. So what happens in this reaction, if you draw the arrow pushing, it is the lone pairs from the sulfur attacks the partial positive carbon, and this bond break. So you end up having chloride ion. So the reaction is relatively easy. It's a typical nucleophilic attack, and has same time have the leaving group, chlorine, breaks the bond. The leaving group, okay, by the way, the leaving group, as you see from the last time, leaving group, it is bond break, and not only bond break, the leaving group, either atom or polyatomic structure, it takes away it leaves with the pair of electrons, which used to be the bonding electron between the leaving group and main structure. So if you look at the this is a little exercise. Okay, this little exercise, and basically identify which one's leaving group, because the leaving group it looks like simply an organic molecule fall apart, but the leaving group it should be the one that the part of the molecule that takes lone pair electrons, and which means the rest of the structure lost the pair of electron and become positive charge. And so you look at this is a ether molecule. Ether molecule under a certain condition can break the bond. I can see, and you can see the final product. This section, it looks like come from that. So this piece, it is the leaving group. And also you can see the oxygen has a negative charge. That's another proof that oxygen and the acyl group together is a leaving group. Not the other way around, okay? Because oxygen is negative charge. This lone pair has to go with oxygen. So the wrong way of the dissociation, it is if the bond breaks this way, what will happen is this carbon has negative charge, and this oxygen should have positive charge. When you have arrow moving this way, it means this structure is a leaving group. But you can see the bond breaking to this direction does not match what you see in the actual bond breakage. So the leaving group between this and this, the one with more negative charge compared with the original molecule, it is a leaving group. So this is a leaving group. Yeah, leaving group is a carry the basically the single bond breaks, and those two bonding electrons now go with the leaving group. So it's kind of if I use a bad analogy, it will be the divorce. If you get a divorce, one of the two parents that keep both kids are the leaving group, and it's kind of bad analogy, but it looks the two part break the bond, and like the family break apart because divorce. Then the parent that is keeping the two kids are the or keep the money. You know, those are the leaving group. Okay, so the substitution reactions. This reaction is typical, as we learned before. Almost all the organic or any reactions in general are reversible. In general, are reversible reactions, and the same as the substitution reaction. It is actually a reversible reaction, and that's why it progressed typically very slow. And so the reaction being reversible, that means to make the reaction happen, which means favor the product, the reactant must be a strong reactant. For the reaction, by the way, for this case, a alkyl chloride react with a hydrosulfide ion. This reaction, it gives us the thiol. Is very similar to alcohol and the chloride. This reaction can reverse, which means the chloride ion can attack back on the carbon and kick out the SH group as a leaving group. So the reaction progress, it really depends on which one's stronger. In general, we define as compare with two nucleophiles. We have the forward reaction. This is the forward reaction nucleophile. And the Nu 2 dot in organic chemistry represent the nucleophile, the one that like positive charge carbons. This is nucleophile in the reactant. For the reverse reaction, the chloride ion is the reverse reaction nucleophile, because the reverse reaction, the chloride ion with a lone pair will attack this carbon and try to kick this out. That's a reverse reaction nucleophile. So for the reaction to move forward, favor the right-hand product, the reactant nucleophile, it must be stronger than the product nucleophile. The reactant nucleophile has to be stronger than the product nucleophile. And so, yeah, in the organic chemistry, we find out sulfur is typically a very strong nucleophile, whereas the chloride is a fairly weak nucleophile. So this reaction taking place just because the strength of nucleophile or nucleophilicity is a big word, but we rarely use those. And this word definition kind of vague. And nucleophilicity is come from the reaction, the study of organic reactions by the organic chemists, not quite from just simply from the atomic structure or pKa, not so much. Okay, so that's nucleophilic reaction taking place, and the chloride being the leaving group, SH is the nucleophile. By the way, the reverse reaction, in the reverse reaction, leaving group becomes a nucleophile, and so it all depends on how you look at this. Nucleophile typically we call it in the reactant. It's part of reactant. Okay, so the leaving group. The leaving group is very important because for the reaction to shift to the right-hand side, the leaving group has to be fairly stable. And there's actually the two things we need to consider. First of all, the leaving group before the reaction. It is part of the structure. Okay, this is the a reaction where you have a nucleophile attack the carbon that is attached with a leaving group. For the nucleophilic attack to happen, this carbon has to have a sufficient positive charge, which means the X must be fairly highly electronegative. So the high electronegativity is one of the factors we need to consider. So for example, if a carbon bond with carbon and someone tried to design a nucleophilic attack, this is not going to happen. This reaction will not take place because this carbon have the same electronegativity. That makes this carbon not really have positive charge. It will not attract the nucleophile. So that's the first thing we need to consider is there has to be high electronegativity. The other thing we consider is the after bond break. After bond break, the leaving group become negative charge, gain a negative charge. So the leaving group must be able to stabilize the extra electrons. So that means the final ion must be very stable, which means this must come from strong acid. The leaving group is better as a conjugate base from a strong acid. For a strong acid, give you the stable, okay? Because the more stable the leaving group, which is typically the anion, means it does not have a strong tendency to take back proton, for example, which means it must be a weak base. Leaving group is better be a weak base. And as we learned before, weak base come from strong acid. And if those of you remember what kind of structure makes a strong acid, then the conjugate base will be good leaving group. So that's the strong acid create a conjugate base, which will be a good leaving group. So remember, it must be a weak base. So here's a chloride is a very good example, because hydrochloric acid, HCl, is a very strong acid. It's one of the strongest, which means the chloride will give us a very weak base. Very good for being the leaving group. And there are many others, like bromide, iodide, the bisulfate ion. Bisulfate ion, it is conjugate base of a strong acid, sulfuric acid. So this is a very good leaving group. And there's more, bromide, iodide, and so forth. So that make a good leaving group. So that's, yeah, pretty much the high electronegativity. These are actually the, in general, the high electronegativity atoms. But even among those series, there's a preference. The preference are chlorine is good leaving group. These are all very good leaving group. And fluorine, nitrogen, oxygen, they are typically not very good, even though they give you stronger acid. Among this whole list, the highly preferred are the halides, because hydrogen with the halide give you the strongest acid. And okay, so these are the strong acids. The strong acid give you the conjugate base. Conjugate base come from strong acid are the better leaving group. Okay, come from strong acid, give you conjugate base of the leaving group. So this is an example about strong acids, hydrohalide, carboxylic acid. Remember, in organic compounds, carboxylic acid, it is most acidic. Next will be the alcohol. Okay, so carboxylic acid, even though among the inorganic are fairly weak acid, but among the organic compounds is one of the stronger ones. The reactant with a leaving group, we call them substrate in the nucleophilic reactions. The one with a leaving group, substrate. And the substrate, very common substrate are the alkyl halides. These are basically the alkane with typically one hydrogen replaced by a halogen. Fluorine, bromine iodine, chlorine, and so forth. Those are the, these have the halides as a leaving group. Halides as a leaving group. And because the halogen have a high electronegativity, the carbon can be attacked by the nucleophile. The naming for the alkyl halides, this will later in the later chapters, toward the end of this chapter, we'll bring back. Naming alkyl halides is fairly straightforward. So the halide as a substrate for nucleophilic substitution, it has depends on how many carbon atoms around the carbon that has a halogen. We have different degrees, different kinds of naming for the location for the reaction. And because this is actually in the nucleophilic substitution, and especially later chapters, we'll bring this up again. This chapter, the carbon in the alkyl halide that is bound with halogen, this carbon has the partial positive charge, is where the nucleophilic attack taking place. The nucleophiles coming here to form bond, and then this bond will break. This carbon that bound directly to the halogens we call the alpha position, is the alpha carbon. It's an alpha carbon. The carbon next to the other carbon that is bound with the alpha carbon is a beta. So we have two beta carbons. The beta position in the nucleophilic substitution reaction is not involved in the reaction, but it does affect the reactivity. So later we'll see that the beta is not really part of the reaction, but influence the reaction. Gamma position is very far away, so we typically don't really deal with it. Gamma position is one step further away from the alpha carbon. And among the halides, when we discuss the halides in the nucleophilic substitution, depends on how many carbon attached to the alpha carbon. How many carbons attached to the alpha carbon? We have primary, secondary, and tertiary. The primary is the alpha carbon. There's only one or none. Okay. When the alpha carbon attached with one carbon, or when the alpha carbon have no carbon attached, both we consider as a primary. That means only one carbon, no more than one carbon attached to the alpha carbon. If there are two carbon attached to the alpha carbon, as in this case, that would be the secondary halides. If there are three alkyl groups attached to the alpha carbon, that would be tertiary. These three types of alkyl halides have a fairly different reactivity in the nucleophilic substitution. So we'll see that later. So simple practice, decide what are the alpha, beta, gamma. So based on the, consider this chlorine, and you treat this as alpha carbon. What are the beta, gamma, and delta? Delta isn't far away, one step further from the gamma. So if you consider this is the alpha, if this is alpha, that one step further away from the halogen leaving group, this will be the beta. And likewise, this will be beta. Oh, by the way, this molecule, the commercial name is lindane. Lindane is was very popular, the insecticides to kill the mosquitoes. When in the last century, in the middle of last century, the Allies, their troops are living in Australia in the jungles with tropical weather. There are lots of mosquitoes. Mosquito spread the malaria and all the disease, and so the authorities use lindane to kill the mosquitoes, and so to suppress the spread of a malaria disease. So that's it's chemical use. And so this is the beta, and this will be the delta, the gamma. There are two gammas, and there's a one delta. It's very far away from the alpha. Beta, gamma, and delta. So these are the A, B, C, D corresponding to the English letters. Further away from the center. Okay, so what are the kind of is the primary? If you look this carbon, okay, now it's kind of messy. If you look this carbon, red dot carbon, is this a primary, secondary, or tertiary carbon halides? What degrees? Primary, secondary, or tertiary? Anyone? You can see this alpha carbon attached to how many more carbons? 1, 2. Do we have more? That's it. Only 2 carbons. So that's a secondary carbon. Secondary carbon. Secondary alkyl halides. And so we'll see some more examples how the degrees affect the reaction. Okay, so finally, this is the official review of the last part of the error pushing in the last chapter. And we have the, actually we first started with the proton transfer. This is the, we learned the first proton transfer. And nucleophilic attack is forming bond. This is form bond. Form bond. Leaving group, that's a break bond. Break bond form an anion. Anion being the leaving group. Rearrangement is the alkyl or hydrogen. Take 2 electrons, take both the bonding electrons, move to a different location. And you see the end result is the copper cation seems to get migrated, shifted. So that's the 4 types. We'll see that in this, we'll see all 4 in this chapter. So the red arrow is showing the bond breaking. And there's also bond forming. The nucleophilic substitution reaction mechanism, quick review, reaction mechanism in the 2nd semester general chemistry refers to how does the atoms or molecules react at the molecular level in the elementary steps. Okay. The elementary steps are actually how the atoms or ions or free radicals form bond or break bond. And the reaction in the nucleophilic substitution, it has both. We have both the leaving group, loss of leaving group, give you the anions, the leaving group, and cation, form a copper cation. Or you have one-step nucleophile attack and attack the copper cations. This is one possible pathway too. This nucleophilic attack is the anion form bond with cation. So in the end, the charge becomes neutralized. The entire molecule have no charge. So very soon we'll find out the reaction. It can be complicated, and we'll go through the one by one. Among all the reactions, the steps, elementary steps, we'll have all 4 types. Depends on what kind of reactions. We might have up to all 4 error pushings. The first one is the easiest, and we have a code name symbol as SN2. The SN2 means it is a nucleophilic attack, nucleophilic, and the substitution is a substitution reaction. It is substitution reaction, S. 2 means is a second order. It's a second order reaction. This reaction, second order, means in this reaction, we have both a nucleophile and a substrate in this rate determining step. The rate determining step. We have both together. And the reaction, the rate law for the reaction, according to the kinetics, we learned in the 2nd semester general chemistry. The rate law for this reaction, it is a rate constant times concentration of the nucleophile, and times the concentration of the substrate. Both nucleophile and substrate concentration affect the reaction rate. And so basically this is the first order for nucleophile, first order for a substrate. Together is 1 + 1 = 2, a second order reaction. So the SN2 is a reaction that depends on both reactant concentrations. because in the elementary step, in the slow step, it has both in the same step. And since both in the same step, the nucleophilic attack and the leaving group bond breaking, it happens at the same time. So that's what we call it is concerted, synchronized, concerted. Bond breaking, bond forming happen at the same time. And that's the SN2 reaction. This reaction is essentially has only one step. It only has one step, and this step is slow. So that'll make it SN2 reaction. And so the reaction bond forming by the nucleophilic attack and the bond breaking of that carbon with the leaving group happen at the same time. And so the reaction happens, pay attention to the stereochemistry. Stereochemistry is actually the this sulfur attacked from the backside. And the leaving group bond breaks. All right, so that's the that is taking place. So you watch the stereochemistry. Methyl group as a wedge, hydrogen as a well, methyl group as a dash, hydrogen as a wedge. After forming bond, you can see the sulfur bonding from the left, and the hydrogens may maintain as a wedge, methyl group maintain as a dash. So this reaction, talking about a reaction, it seems like we call it inversion. Inversion, and inversion means if the leaving group and the nucleophile in the ranking according to the SR system, the SR stereochemistry system, they have the same ranking, then you start from S, the reactant substrate to S, enantiomer. After reaction, the nucleophile being very high up in the SR ranking system, it'll cause the molecule becomes R. So those of you, well, you can quickly practice on the S and R designation. Put the hydrogen as the lowest, furthest away from you, and you start from the highest ranking to the number 3 ranking. If you get a clockwise, you go to R. Counterclockwise, you gotta get S, and so forth. Do a quick practice, you notice this start from the S small s configuration, but the reaction product gives us the R configuration. By the way, in the real SN2 reaction, it really depends on how the ranking of the nucleophile. Okay, the S and R, we call it inversion, may not necessarily taking place. If your nucleophile is very low ranking, you may not have. You may not see the S to R or or R to S transition. Just keep in mind. Okay, so the very important for understanding the stereochemistry is the reaction happens from the backside, from the other side of the leaving group, So we'll see that better in the next animation. This is substrate. So this was a substrate with the green atom as a leaving group. This is the nucleophile, come here attack. So that's what happened in the reaction. That's what happened. The substitution is come from the back-hand side. This is the transition state. A transition state in chemistry, we use a double cross and put them in bracket. at this point, this carbon is not octet. You have 2 bonding electrons here, 2 more bonding electrons, so the together have 10 electrons, valence electrons, and it's more like a trigonal bipyramidal. This configuration is trigonal bipyramidal. The SN2 reaction, because reaction taking place, the reaction is one step. Okay, both reactant are fairly stable. That means the reactant will have a very low energy, which means for this reaction to become product and transition state being the high energy state, you have a fairly large activation energy barrier. You have a large activation energy barrier. So that means the reaction is typically very slow. You have very large activation energy barrier. And if you remember from the energy chapter, the reaction can be, there are 2 classifications, 2 types of chemical reactions. First is the thermodynamic controlled, and the other is kinetic controlled. Kinetic control is easy to understand, is a low activation energy, reaction fast. Thermodynamic control means it's slower reaction, but the final product have lower free energy, which means you have a very large equilibrium constant. Thermodynamic controlled reaction have very large equilibrium constant. The equilibrium constant. But the rate constant, which means how fast the reaction, this might be slow. So which is true for the SN2 reaction. It is a high energy barrier, so slow reaction, very, very slow. But the reaction to become product, the driving force, it has to be the large equilibrium constant, which means give you long enough time, the reactant should all become product if the free energy decrease is large enough, highly exergonic. And so that's the SN2 reaction. It's slow, but driven by the free energy difference. The rate constant, or the reaction rate for the activation energy in the past, when we studied the general chemistry, we normally did not mention about how big, what makes the activation large or small. We rarely mention this, except we mentioned maybe if to break a multiple bond in the reactant, let's say in the reactant we need to break a triple bond. That's fairly unfavorable. You have very large activation energy. But typically we don't mention about activation in the general chemistry. In organic chemistry, there are some real, tangible, easy to remember factors that affect activation energy, and we should know. In the SN2 reaction, there are nucleophiles coming to attack the carbon, and the steric effect, which means how accessible for the reaction site to the nucleophile, it can be easily evaluated. So what do we find out the SN2 reaction? Compared with the different degrees of the alkane and alkyl halides, their reaction rate completely have a tremendous difference among those different degrees. Primary, the primary halides, these two both are primary. The methyl halides even more open. There's no beta carbon present. The methyl bromide have the fastest reaction, SN2 reaction, given the same condition. It's about 10 times faster than the primary. Both are very, very fast. The methyl, it is a very special primary with no beta carbon, all just simple hydrogens. Very fast reaction. You move on to the, when there are two alkyl group, two methyl group on this alpha carbon, this gives you a secondary. So secondary reaction is much slower. So basically these two reactions at least 100 times faster than the secondary reaction. And the tertiary, when there are three beta carbons attached to alpha carbon, the reaction is even slower. It actually, as a matter of fact, is so slow, not measurable. The reaction negligible, no reaction, basically. No reaction for the tertiary alkyl halides. And so the explanation is, okay, this is the with the 3D, with sort of 3D structure shows you the difference among those alkyl halides. We just ignore the tertiary carbon because no reaction. The activation barrier is too high. So what happened? What is different between these three halides? It is when you have a primary, the methyl halides, each one being hydrogen, very small atom, so make it very easy for the nucleophile to attack, to access, and to attack. When this alpha carbon have one methyl group, and with two other being hydrogen, this methyl group with all the hydrogen bonds sticking out, make it a little more difficult, tricky to get to the nucleophile, to get to the carbon to attack. So you can see that this can explain the difference. The methyl halide is about 10 times faster than the, this kind of primary ethyl halide, 10 times faster. Well, if one hydrogen replaced by one more methyl, these are, remember there how big they are. This is how big they are. That means it becomes much harder for the nucleophile to attack this carbon. Because these two, the two methyl groups, almost like a shield. You start with one shield, it still can be attacked. But if the structure of two shields is much harder to attack. It's almost like warriors. The warriors, if you watch those medieval ages fighting scenes, the warriors knight have the shield. One shield can attack single arrow. It can do some effect. If you have two shields, you pretty much cover yourself very well. It's very hard to attack. Similar to that. So the difference in the reaction energy profile is from the methyl halides to the ethyl halides to the secondary halides, the activation energy barrier become higher because nucleophiles are having a harder time to attack. Bigger barrier will slow down the reaction. Tertiary is literally will not allow the nucleophile to attack because there are three big methyl groups around. It blocks the whole entrance. No more entrance to attack. And so that's okay. There's something interesting. This is the this compound we call neopentyl because there are 5 carbons. It is a pentane. This pentane name we call it neopentane. This carbon has 5 methyl groups, 4 methyl groups attached to central carbon. This carbon is basically the quaternary carbon. And with one of the hydrogen replaced by the bromide, it gives us this compound. This compound, if you look at this carbon is going to be the nucleophilic site because it's a partial positive charge. And so the nucleophile should be able to attack. And so keep in mind there are hydrogens here, hydrogen here. So nucleophile attack, it has to go on the backside, go this way to attack. And this bond breaks. But the question is how quick this reaction, or how easy it is for this reaction to take place. If you look at this carbon, it has only one beta carbon. That looks very promising. This carbon, by the way, it is a primary carbon. It's primary. Well, the primary carbon, based on the last few slides, it should be decent reaction. Not too fast, but definitely better than the secondary. But think about those. There are three methyl groups. How does those three methyl groups will really impact or not? Now you have three methyl groups, and each methyl group has 3 carbon bonds. So the actual shape for this, with hydrogen being considered, you get a very chunky. It is basically a single shield, but this shield is like an oversized, a humongous shield. A humongous shield. That actually makes it hard for the nucleophile to attack. It's almost like, if you draw an analogy, the warriors in the Middle Ages have one shield to protect themselves with the one shield. And we know the same warrior if have 2 shields, that's a great protection. 2 shield can protect them from both sides attack. Very good. Well, this new pentyl, it is the same warrior carry a gigantic shield. This gigantic shield is going to be very good to protect themselves. So with this new pentyl, even though the carbon, alpha carbon is the primary carbon, the third butyl group, which way, by the way, this is third butyl group, it is very large. It is basically too big for the nucleophile to go through, to attack. So this is kind of one of the exceptions. If you just look at the previous slide that shows you the methyl being the fastest, and then primary alkyl halides being fast, and then the secondary be very slow. You can see this is actually a situation. The carbon's primary carbon has only 1 carbon connected, but the single beta carbon is not some normal beta carbon. It is third butyl. Third butyl, if you remember, in many cases have very strong steric chemistry effect. It's kind of dominate the whole picture. It's like a big boss. The big boss decide what kind of position to take. And so that's typical pattern. It should be the primary faster for the SN2 reaction, primary faster than secondary, then it's much bigger than tertiary. This have no reaction actually. But keep in mind the primary, it really depends on what kind of beta carbon. We have a big chunky third butyl as the beta carbon. It might block the reaction, slow down reaction completely. So that's what is steric effect. SN2 reaction, keep in mind, SN2 reaction strongly prefer for the primary carbon. It's much easier to go through the SN2 reaction.